Hello guys, in this video we are formally going to see what is vector spaces. Okay, so nowadays due to this pandemic, the corona pandemic, when I came into my university back from my home, I was told to be in a quarantine for a period of 7 days. So here am I, so this is me. I am told to be in a room for 7 days. I cannot move out of the room. Okay, so this is my space now. I can only be in the room. This is the only space that I can acquire. So I cannot go out of the room because the door is closed. Okay. So I'm formally trying to give an motivation to the vector space now. So I am inside this room. So this room is my space and I'm closed under the door. So if I open the door, then only I'll come out of this space. Or else, if the door is closed, so this is my space. So this is my space closed under the door. So a very similar example to the vector space is what I have shown that. So now what is a vector space? Take a set V. So now this set V can be anything. It can be a polynomial, it can be matrices, it can be continuous functions, anything. So this I have explained in my previous video of abstraction, right? So take a set V. So the set V is analogous to the room over here. Okay. Now you can add any two elements from V and you get some other element that is in V. So take any two elements from this set V. So if you consider polynomials, take any two polynomials of a degree less than equal to n. Okay, you add both of them. Okay, acha. You can also use a scalar that comes from a field. So now there is some other thing that is field. I've explained this in my first video. And multiply the scalar with these vectors, you still get an element in V. So the whole story is you take any two vectors, that is any two elements from V, you multiply them with the scalars that come from a field, you add them, and you get some other vector V3, which is again inside the V, the set V. That is, no matter what you do, you will always lie inside this box. So this is very similar to that corona example, the quarantine example. So no matter what I do, I will always be inside the room until and unless the door is closed. So over here the door is plus and multiplication, scalar multiplication. So the vector space says that if you add or do a scalar multiplication of any vector that comes from a set V, then you will always land up with some other vector that is in set V. You will never come out of this set. That is the whole theory of vector space. So this is by vector space they say that this is the space of the vector. It will always lie in this space. Okay, so for the different sets that you have, the spaces will be different. So this is what is vector space. Okay. So now let us see the formal definition for the vector space. So take a set V. Okay, you add any two elements of V, you get some other element that is in V. So you add any two elements, you will always get an element in V. You can also use a scalar that comes from a field, multiply it with the scalar, you still get an element of V. So that's the whole theory. And you have some more properties. Now let us discuss the properties. Right, so first we'll see the properties related to addition. So this we know it is closed under addition. That means any vector you add any two vectors, that will always be in the set V. So other property, x plus y is equal to y plus x. So that is it should be commutative. The vector, if you add two vectors like this, x plus y or y plus x, it will be same. Next, associative. So if I add these two vectors first, that is I add y plus z first and then I add x, this is same as I first add x plus y, I first add x and y and then I add z. So both of these are also same. So this is associative, right? Now let us take an example to understand the others. So let me say that the set that I'm using is R2. So that means that I can pick up any vector that is two-dimensional. So it is a point basically. So if I pick a point over here, so it may be say 1 comma 1. So 1 comma 1 is a point in this space, R2 space. So R2 is my two-dimensional space. Any point you pick up in this two-dimensional space, that is my set V. So it belongs to R2. R means real numbers. So real numbers. I can pick up any two real numbers. That will be my set V. So the vector looks like this, X and Y. Okay. Now, uh, okay. So now let A and B be two scalars that also belong to the real number. So over here, the field is real number. So whenever you talk about the vector spaces, three things should be in mind. One, that what is your set V? So over here, V is the set R2. Next, what is the field? So over here, field is the set of real numbers. And third, that what are your, what can you do? That is, you can add or you can multiply. So it is closed under addition and multiplication. These are the points. Okay. So let's see the other properties. So there should always be a zero vector. This is important. So there should be a zero vector in a vector space. So what does this zero vector actually say? So the zero vector says if you take any vector from the set V, so this A is a vector in the set. So I have choose the R2 as my set V. So A becomes any point in this space. So for instance, it is say some x comma y. Okay. So whenever I add this A with the zero vector, I will get the vector back. So this is what is known as a zero vector. So A plus 0. So I have made this bold because it is a zero vector. Okay. It is not a zero scalar, but it is a zero vector. Okay, so this is what I mean by a zero vector. So now a zero vector should always be present in a vector space, a very important property. Next, there must also be an inverse for every vector. So what do I call an inverse is, so for every A there should be a minus A, such that when I add both of these, that is A and minus A, the addition gives me 0. Quite simple. So the addition of two, if they are giving me 0, and this 0 is the zero vector, it is not the zero scalar. So if they give me the zero vector, that means both are inverses of each other. So A is an inverse of minus A and minus A is the inverse of A. So that is, and this is what is known as an additive inverse, because this inverse is by addition. So this is additive inverse. And 0 is also known as the additive identity, because whatever you do, so if whatever you add in 0, you will always get the same thing back. It will not change the A. So hence it is known as additive identity as well. Okay. Now let us see what are the properties related to scalar multiplication. So let's say I have alpha and beta which belongs to a field F. Okay, alpha and beta are scalars that belong to the field F, and x and y belong to the they are the vectors, they belong to the set V. So these are closed under scalar multiplication, we know that. So if alpha belongs to the field, so alpha into x will belong in the set V, because x belongs to set V. So you multiply it with alpha, it will again belong to the set V. Okay, now let us see the properties. So if I first multiply alpha and beta, and then this thing is multiplied by x, this is same as I multiply beta first with x, and then this thing is multiplied by alpha. Okay, So actually, by just looking this thing actually looks very simple, but there is a slight difference between what is happening over here and what is happening over here. Let me tell this to you with an example. So over here, alpha and beta are scalars. So by scalars, there will be just a uh, a number. Okay. So actually, this is with respect to the field, but let's say for now, I assume that the field is a real number. Okay. So let me say that the field is reals r, and my set vector, the vector set is r squared. Okay. So now if you see alpha and beta, there'll be numbers. So there'll be some 2 or 3 something. So let's say it is 2 into 3. Okay. So this is what is known as a scalar multiplication. So 2 into 3 will give you 6. So this is the scalar multiplication that is happening over here. But then when you multiply this thing with x, so now x is a vector. So x will be of the form something like this. Say 3, 4. Okay, so this is x. So x is a vector, and now multiplying say 6 with this means you have to multiply 6 into 3, so that is 18. And sorry for my handwriting. And 6 into 4, which is 24. Right. So this is right. So this is scalar multiplication happening over here, and this is the vector multiplication. I mean, so this multiplication over here is a vector multiplication, and this is a scalar multiplication. On the other hand, if you see over here, this beta into x, this is a vector multiplication because x is a vector. So it'll be some beta scalar into the vector x. So this is a vector multiplication. And this alpha into this thing is again a vector multiplication, because uh, beta into x now becomes a vector, something like this. So alpha into a vector will again make it a vector multiplication. Okay, so this is the main difference between the things that are over here and the things that are over here. Over here, there is a scalar multiplication that is multiplied with the vector. Over here, there is a scalar multiplied to vector, so there is a vector multiplication and then again a vector multiplication. Okay, so this is a very important topic, a very important point to understand, which most of the people forget. Okay, the next thing. So now alpha plus beta into x. Okay, this is equal to alpha x plus beta x. Now again, the same principle. Over here, alpha plus beta, this thing over here is a scalar addition, because alpha is a scalar, same 2 plus 3. So they'll give you 5, but this is scalar addition. And this scalar addition is then multiplied with x, so that is a vector multiplication that takes place over here. But if you see this, so there is alpha into x, which is a vector multiplication, beta into x, which is a vector multiplication, and then two vectors are adding. So this is a vector, this is a vector. So this is a vector addition. So please note that. So this is a vector addition, and this over here is a scalar addition. Okay. And the same thing applies over here. This is a vector addition over here, and this multiplies over here. So this is a vector again. A vector multiplication. Then over here, this is a vector multiplication, a vector multiplication, and a vector addition. Okay, so please keep this in mind if you go into intense topics, or if you are into research, then these small things will help you a lot. Okay, so please understand what operation is going on. So this is a scalar operation, a scalar multiplication, a scalar addition, and this is a vector addition. Okay, so if one is from a programming I mean from computer science field, then he can also understand it better, because what happens is, say if you're from very basic programming, so you know that 2 into 3 is just a basic multiplication operation. But then if you want to multiply, say, this 6 with a vector, so what you'll have to do is, say you'll have to run a for loop. So for 1 to 2, do this multiplied by 3, and then this multiplied by the second element, like this. So hence these two things are different. Okay, so please keep this in mind. Okay, so the next important thing is, so as we had the additive identity, we have the multiplicative identity of the field. Okay, because we can do only multiplication with the field, there is no vector multiplication allowed. So hence we have the multiplicative identity of the field. So that is 1f. So I'm denoting this multiplicative identity as 1f into x should be equal to x. So the definition of multiplicative identity is, whenever you multiply it with this vector, you get the same vector back. Okay, so now please keep this also in mind. This 1f does not necessarily mean that it will be 1. Okay, so this means it can change with respect to the field. For instance, if your field is a set of real numbers, then 1f is equal to 1, then there is no problem. Okay, but if your field is a set of complex numbers, then 1f is nothing but 1 plus 0i. Okay, so this is very important. It is not 1 plus 1i, but it is 1 plus 0i. Okay, so with respect to the different fields that are out there, your multiplicative identity can change, and it is not necessary always 1. Okay, so that is also something that you'll have to keep in mind. Okay, let's go to the next slide. So with this we have come to the end. So if you go through the, I mean, summary, so it is, it is the 4 things that is important for a vector space. So that is the set V. So what things that you have to ask if somebody gives you a vector space? So first is the set V. What is the set, the vector set? Next is the field, from where can you pick up the scalars? Then what it is closed with, so it is closed with addition and it is closed with multiplication. So that is a definition of the vector space. Okay, and the elements of set V are called as vectors. So no matter if, say, your set V is matrices. Okay, so they may be, say, matrices of say some n cross m matrices. Okay, still if you are into vector spaces, I mean, if you follow these notations, the vector spaces literature notation, then these matrices will also be termed as vector over here. Okay, because this is because, to just to make everything on the same line, because this thing is now representing a point in the set that is over here. Okay, so that was all about vector spaces. I hope you have understood. Thank you so much for watching. Thank you.